me, Rui, and today's video is an introduction to chemical equilibrium.
Hi everyone, let's start at the very beginning. It is a good place to start with that tendency in the universe away from order and toward chaos. This is summed up in that second law of thermodynamics. There's a tendency away from organized matter to chaotic matter. The idea that increasingly disordered particles are favored. Just think of a teenager's bedroom, for example, going from order to chaos. We call this chaos entropy, or disordered particles. There's also a tendency from concentrated energy to diffused energy, so that exothermic reactions would be favored. Those are the ones that reduce stored energy. This first tendency, the one that we called entropy, or increasingly disordered particles, that's the universe favoring maximum disorder, or maximum entropy. And of course, the one with diffused energy, that's minimum enthalpy. Look, let's see a couple chemical reactions to determine these effects. So this first reaction here is the combustion of liquid ethanol. So there's the ethanol, oxygen gas. We know that if we get the balance right here, we'll produce some carbon dioxide and water vapor and energy. If you look on the right-hand side of this reaction, you can see quite a few more gas particles banging around. They're very chaotic, less stored energy. So this reaction, we'd call it spontaneous in the forward reaction. Both tendencies are driving it to the right. Here's a second reaction where carbon dioxide and energy are where carbon dioxide is being decomposed with energy being added. There's more chaos on the left of those gas particles and less enthalpy, less stored energy. This reaction we say is spontaneous in the reverse reaction. Here's a third reaction. This one here is the decomposition of calcium carbonate. And this one here is an endothermic reaction. It requires 180 kilojoules to do. It produces the calcium oxide and CO2 gas. Notice this special double-ended reaction arrow sign. We'll talk about that in a minute. On the right you have more chaos, the gas particles. On the left, minimum enthalpy. So this situation here, what we call an equilibrium system, can arise when those two tendencies, the tendency towards chaotic particles and the tendency towards diffuse energy, if they are acting in opposite directions on the reaction. In this case, they are. That idea that maximum entropy and minimum enthalpy are acting on either sides of this reaction to drive it in two different directions. You can get this kind of equilibrium system set up. So let's characterize what an equilibrium system looks like. You know the word equilibrium already, and most people would agree that it suggests to you a sense of balance or equality. In this case, it's balanced or equal rates. Which rates? It's the rate of the forward and reverse reactions. And it's a dynamic equilibrium. Think about that. Particles reacting in the forward reaction and the reverse one simultaneously. The balance is a balance of rates. The equality is an equality of rates. So here's a simple reaction that'll give you an example of such an equilibrium system. This one is just a sealed beaker. We'll put a lid on it, have some water inside. And this liquid water, if you add some energy to it, can make gaseous water. And of course, go back the other way in condensation as well, releasing energy. There's the particles evaporating. You can see them condensing there on the top of the container and rolling down. If you wait for a while, these rates will become equal, and the equal condensation and evaporation rates tell you that this system is in equilibrium. So let's look at some characteristics of an equilibrium system then. We'll use this one as a good example. First of all, it's pretty clear that the macroscopic or large-scale properties are pretty constant. If you stand back and look at this, not much seems to be happening. Also, typically it's a sealed system, otherwise mass would escape. That's a macroscopic property. Finally, if you zoom in on a molecular scale, there's quite a lot of action. So those are the three main characteristics of an equilibrium system. Let's have a look at the next two videos in this playlist for more on the topic, and stay tuned for our next lesson in Chemistry 12, which is Le Chatelier's principle.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!